Hello, happy May 4th. Today we're going to be looking at how climate change is expected to affect tropical cyclones in the North Atlantic Basin, with a more specific focus on the Outer Banks region of North Carolina. We're going to start with a high pass overview of the relevant materials just to make sure we're all on the same page. Tropical cyclones are known by many names around the world, such as hurricane or typhoon you might have heard. However, they all have the same key features. Tropical cyclones are synoptic scale features that exhibit persistent, organized convection around a low pressure system in tropical or subtropical waters. They have a closed cyclonic circulation and are non-frontal. Tropical cyclones are seasonal, but they are possible all year round if conditions are correct. Tropical cyclone season in the North Atlantic is June to November. They are mainly steered by the flow associated with subtropical anticyclones, like the Bermuda High in the Atlantic. On the right here is how tropical cyclones are classified in the US. We use a system based on wind speed. Categories 3 or higher here is classified as major hurricanes if you hear me refer to those. There are 5 main ingredients needed for tropical cyclone formation, but just because they're all present does not mean a cyclone is going to form or necessarily persist. Warm sea surface temperatures are needed as the ocean provides heat and moisture in the form of enthalpy fluxes, which provide the energy for the storm's winds. It's better if the water is heated to a deeper depth, so that when the storm brings water to the surface, which we know as upwelling, it's not colder. A large low tropospheric cyclonic rotation provides the locus for convection to organize around. Conditional instability over a deep layer of the atmosphere allows for thunderstorm formation. Weak vertical wind shear keeps the tropical cyclone from tilting and being ripped apart. And large lower to mid-tropospheric relative humidity ensures that the energy from the ocean can go to strengthening the winds and not just priming the air for thunderstorm formation. When I discuss climate change in the following material, it's important to recognize that the climate we have in the future will be human influenced. Climate does vary naturally. We see this in that graph of CO2 concentration dating back to 800,000 years ago. There are peaks and there are valleys, but it's never gone around 300 parts per million before. And yet now we see, after the Industrial Revolution, a sudden jump to we're now at 421 parts per million. Human influence is unmistakably the dominant cause of observed global warming today. We're going to see the consequences of this manifest in many different ways, from heat waves to sea level rise to drought and to flooding. We know that over 3 billion people so far live in contexts that are highly vulnerable to climate change. When we model climate change, there are a variety of emission scenarios that can be used, which makes comparing studies sometimes difficult. The studies that I'm going to reference in this mainly use RCP 4.5 or RCP 8.5, which refer to the level of radiative forcing resulting from the scenario in the year 2100. The Outer Banks are a group of barrier islands that stretch around 175 miles along the coast of North Carolina. They're low-lying and therefore particularly vulnerable to flooding and beach erosion. They are also uniquely located where the U.S. bumps out into the ocean. As tropical cyclones flow around the Bermuda High, they are not likely to make landfall on somewhere like the Georgia coast where it curves in, but somewhere like the Carolinas just based on pure geography. The Outer Banks has seen around 20 direct impacts from tropical cyclones since 1980, and I've listed some of the notable ones here you might recognize. The other thing I'd like to point out here is the climatology of precipitation at Cape Hatteras, which is part of the Outer Banks. There's a clear increase through hurricane season, which is likely due to both tropical and non-tropical precipitation patterns. This could exacerbate flooding issues the area faces. First, I'm going to step through how the 5 major ingredients I laid out are expected to change with climate change. So this chart shows the projected change in sea surface temperature. We see warmer temperatures everywhere, but especially at higher latitudes. If water stays warmer to an appropriate depth, the energy tropical cyclones need to maintain or even intensify can be found at higher latitudes. Thus, we might see a poleward extension of cyclone tracks or where they reach their highest intensities. Relative humidity is the amount of water vapor a parcel of air contains compared to the maximum amount it can hold, which we call saturation. Specific humidity, on the other hand, is a measure of how much moisture is in the air, irregardless of saturation point. Specific humidity is projected to increase, but there's disagreement in literature and observations whether relative humidity is going to increase or decrease. We know that the Clausius-Clapeyron equation tells us that for 1 degree Celsius of warming, we need water vapor to increase by 7%, for relative humidity just to stay the same. The figure on the left shows the observed relative humidity worldwide from 1981 to 2020. We do see a decrease in relative humidity over time, even as the amount of moisture in the air increases because the temperature is also increased. However, this is globally averaged over both land and sea across all basins. The figure on the right is from a study projecting changes in tropical cyclones, but for strong La Nina conditions. We see an increase in relative humidity over the climatological tropical cyclone formation area, but strong decreases over South America and at high North American latitudes. So more research is needed in this area to determine exactly how relative humidity is going to change for each basin and for each time. Higher vertical wind shear values are detrimental to tropical cyclone development and strengthening. Likewise, lower values of vertical wind shear are more conducive to tropical cyclone development. Vertical wind shear is highly variable and dependent on many other surrounding weather systems. However, the position of the subtropical jet can impart vertical wind shear. The further south the subtropical jet is, the more likely it is to impinge upon the tropical cyclone. However, in a future climate, the subtropical jet is expected to shift poleward with the poleward expansion of the Hadley cell, which is shown here. That would decrease the risk of the jet interacting with the cyclone and decrease vertical wind shear. Again, the figure on the right is only for strong La Nina conditions, but we do see the decrease in wind shear in the future climate. As mentioned, cyclonic vorticity centers are needed for the organization of tropical convection. We see this manifest in tropical cyclone seeds. Both frequency and survival rate of seeds influence the number of tropical cyclones that form in any given season, and there is evidence that survival rate is more important to the overall number of cyclones rather than the sheer number of disturbances. The top figure here shows tropical cyclone seeding frequency with global mean sea surface temperature change when present on the abscissa. The black bar is 0 degrees sea surface temperature change, or the same as the current mean sea surface temperature. Purple here is 15 degrees Kelvin cooler, blue is 10 degrees Kelvin cooler, green is 5, and then our red is 5 degrees Kelvin warmer. There's a clear decrease in seeding frequency with warmer sea surface temperatures, which is what we're going to expect under a warmer climate. But we do see a slight increase in survival rate. There's still uncertainty in the scientific community whether the total amount of cyclones are going to increase or decrease in a future climate. It's been suggested that survival rate has more of an influence on the amount of tropical cyclones in a year, but seeding frequency can't be discounted altogether and might actually account for the projected mild decrease in global cyclone frequency. The studies that model an increase in tropical cyclone activity did not change the seeding frequency and actually kept it the same as it is today. However, it's important to point out that these studies that I'm talking about focus on changes in global frequency, not basin frequency, and the numbers and meteorology vary greatly by basin. Researchers Klutschbach and Wood found a shifting of the global base state to more La Nina-like conditions, which favor tropical cyclone development in the Atlantic, but might suppress it in the western North Pacific, which is where we see currently a lot of our cyclones occurring. So if we have a decrease in those in the western North Pacific and an increase in the Atlantic, it might lead to an overall mean decrease, but that doesn't mean we're going to have less in the tropical North Atlantic. This is in agreement with Senya et al.'s figure, which is here on the bottom, which shows an increase in cyclonic vorticity in the area of development for our North Atlantic tropical cyclones. There have not been any studies that I can find conclusively outlining the changes expected in conditional instability, but I can tell you it relies on two things. It's a function of temperature and moisture. There's evidence in both observations and modeling studies that the top of the troposphere is warming more than the surface, which would create an environmental temperature profile that warms with height, essentially creating an inversion, which would prohibit convection and limit the growth of thunderstorms. However, increasing moisture content near the surface through increased enthalpy fluxes would actually make the atmosphere less stable. And I'm just gonna show you this to help conceptualize that. It's extremely idealized. The red line here is the temperature profile T, and TD is our temperature dew point, and it's going to be our measure of moisture. So here on the left, it's around 22 degrees Celsius, which results in an LCL around 950 millibars and an LFC around 850 millibars. If we increase the moisture, say we shift TD at the surface to the right to 26, Now our LCL is around 975 millibars, and our LFC is around 950 millibars, and our EL is higher, which in combination with our lower LFC creates this area of additional CAPE, which is our measure of instability. A moister atmosphere can also mitigate negative buoyancy influences that we would expect through entrainment of dry air associated with vertical wind shear. Now that we've gone through the ingredients that we need to make a tropical cyclone, let's look at the impacts that they bring when they make landfall and how we expect those to change. So flooding is the number one hazard associated with landfalling tropical cyclones, and the largest contributor to that is storm surge. Storm surge is the wall of water pushed to shore by a hurricane. It combines with the local tide and waves to form storm tide. Storm surge is highly variable. It depends on the winds, the pressure, the shape of the coastline, even the depth of the shore. Even relatively weak storms like categories 1 and 2 can produce significant storm surge. Sea level rise exacerbates this risk by raising the overall background state. So if a pool is filled to its very, very max, even a little bit of extra water is going to cause it to spill over onto the pavement. There's no question the sea's rising. From 1901 to 1971, there was an average rate of increase of 1.3 millimeters per year globally. From 2006 to 2018, that was 3.7 millimeters per year. The sea is projected to continue to rise, causing what today would be 100-year flood events almost annually, and over half of gauge locations by 2100. For 1.9 greenhouse gas scenario, we're expecting a quarter to a half of sea level rise of a meter, projected by 2100. Under a high emission scenario, we could see up to a meter of sea level rise by 2100. It's important here that you understand that a millimeter of sea level rise does not equal a millimeter of shoreline loss. So if we're talking about 3.7 millimeters per year from 2006 to 2018, over the last 20 years, areas of the Outer Banks have retreated 200 feet, and they continue to lose beach at approximately 13 feet per year. The loss of shore is again going to make the communities that live on these islands more vulnerable to the encroaching sea. Another factor associated with flooding is, of course, precipitation. Precipitation amount at any given location is going to vary dramatically with any given storm, as it depends on storm size, speed, duration, as well as just geography of the area. Rainfall rate, however, is much easier to compare across storms or across the same storm. Of all the tropical cyclone metrics, rainfall rate has the most robust projected increase. The moisture for a tropical cyclone rainfall comes mainly from moisture convergence, which scales from total moisture content. As discussed, total moisture content is projected to increase in a future climate, so we can expect rainfall associated with tropical cyclones, all else held constant, to increase. That increase isn't just with hurricanes, but with all sources. Extreme precipitation is likely to become more intense and also more frequent, making soil moisture contents higher and flooding even worse. When people think of tropical cyclones, we typically think of intense winds associated with a hurricane. They are a hallmark of a tropical cyclone, and while they're not the leading cause of death, they are still extremely dangerous, and they're how we measure the overall intensity of a tropical cyclone. In recent decades, the proportion of tropical cyclones reaching category 4 or 5 has increased 25 to 30% per degree Celsius of warming. That trend is projected to continue. I specify proportion of hurricanes here because, again, there's disagreement over the total number of hurricanes in a future climate, but there is agreement that the amount of strong hurricanes relative to the amount total that there will be is expected to increase. And no, there's not going to be a category 6 hurricane. And we're not likely to expand the enhanced Fujita scale for tornadoes. At some point, you can't do any worse damage. But the increase in global average intensity is consistent with PI theory, which predicts this increase in a warmed climate. Our image at the bottom here shows the projected increase in potential intensity for a La Nina scenario, which, again, I want to point out is not unreasonable considering Clutchbox and Wood's finding of a more La Nina base state. Our figure from the right here is from their paper examining the shifting of frequency and intensity in a future climate. Now, the changes exhibited in this figure are ones that have already happened. More saturated lines here are statistically significant. A is the change in named storms. We do see an increase in the North Atlantic and a decrease in the Western North Pacific, which I mentioned earlier as a possible consequence of a more La Nina base state. I also want to point out G on this image, which is the percentage of Cat 4 and Cat 5 hurricanes, and we see an increase in every single basin. Now, it's not statistically significant, but there is a known challenge of ascribing statistical significance to changes in hurricane climatology up till now, which is that the quality and length of our data record is not long enough to be able to get those results sometimes. We didn't always have the tools that we have today. The other issue is that a lot of the climate change effects that we're expecting, we wouldn't necessarily expect them to have manifested yet, but we do expect them to manifest in the future. There is no consensus in the literature over how the tracks hurricanes are going to take will shift. There is a discussion of a possible poleward extension of North Atlantic hurricane tracks due to more favorable conditions persisting at higher latitudes like sea surface temperature, but there's also the possibility that weaker easterly winds and atmospheric circulations could shift the tracks east and lead to fewer landfalling tropical cyclones. Again, I'd like to point out these charts of return periods. We see lower return periods where the continent juts out into the Atlantic, like the tip of Florida or Louisiana or the Outer Banks. Given what we've discussed today, it is possible for us to see maybe an increase in return period for a hurricane along the Outer Banks, which is our top image here, but maybe a decrease in return period for a major hurricane, which is our bottom here. So only time and future research will tell. Finally, I'd just like to set the math and core atmospheric sciences aside for just a second and briefly touch on a social aspect, which is the expanding bullseye effect. A storm can only destroy what is there, and increasingly we've been placing more and more in the way of these storms. Listen, I get it. I love the beach. I love the ocean. But it's an undeniable fact that a hurricane can only destroy a house if that house exists. Damage totals might increase irregardless of changes in storm intensity. So this figure here shows an identical path of a tornado and how much more damage it would cause in 2100 versus today. You can see the increasing amount of densely populated areas, which is represented by the red and orange, within that path as time goes on. The Outer Banks is not immune to this. On the right here is a picture from an airplane tour of Nags Head around 1980. You see a few houses, maybe a store. On the left is the same area of Nags Head in 2024 via satellite imagery. Just to orient you, there's two roads here running parallel to the shore. Here are those two roads, and then this inlet from the sound right here and right there. It's the same area, and we see significantly more development now. I'm going to leave you off with some family photos from my trip to Kitty Hawk, where the first motorized flight took place, right there in the Outer Banks, first in flight. It's a historic and beautiful place, and unfortunately, the risk of tropical cyclone-related impacts is likely to increase as our climate continues to warm. Thank you.